you see in front of you is the legendary Soundcraft LX7 mixing console. It has 24 channels of input capability that can feed out to really any number of power amps to handle the sound mixing for rooms from large to small. In each of those channels, you see the array of controls and buttons and faders that can be combined together to individually shape the sound on each one of those channels before it's fed into the output mix. That's what you see in the middle of the picture, the red and yellow and black faders. Those are your main outputs. And so you mix all the incoming channels in and send them out to your power system in order to power the output speakers in your room. And why are we bringing this up? Well, because this is a good example of a matrix that is going to contain multiple different values. On each one of those channels, I could have any of those knobs set completely different from the other channels. Just the volume itself. I may raise the volume of some of the channels over and above the volume of others in order to mix the sound properly. This gives us a good tool, something to visualize a multi-dimensional array with, and that's what we're going to talk about this week. When we get into more advanced programming, what we're doing with those programs is modeling reality. We are taking real-life objects and modeling them in a computerized fashion, and what that requires is more and more complexity in our data structures. When we look at that sound mixing board, we could visualize that a couple of different ways. Each one of those channels, for example, could be a single array, and that array would have, the 10 or 15 different controls that are available on each channel, and we could set, say, as integers, set those from 0 to 10 or 11, depending on the model of the mixer. And then we could have array 1, array 2, all the way up to array 24. Or we could define a structure, define a record for each of those channels, which would make it simpler to model the on-off switches, the mute and the PFL switches, those types of things, as booleans combined with integers for the slider and the pot values. So we've got a couple of different ways that we can do that. The downside of those methods is that we would have 24 different arrays that we have to manage. We would have to declare them, manage them, ensure that they don't overrun their boundaries, all of those different types of things. If we go back and look at that picture, remember that we have neat rows and columns, and they're all the same. And in a data modeling situation, that makes it an ideal situation in which to use a multi-dimensional array. A multi-dimensional array is really just an expansion on what you already know about single dimension arrays. When we declared a single dimensional array, say the 4 integers that you see in front of you, we declared array 1 to contain integers, and we said it has 4 spaces in it. When we move to a multi-dimensional array, we retain that concept and we add a second axis. So if we look over at the table to the right, we see that we have a 3 by 3 multi-dimensional array. The nice thing about the multi-dimensional array is that it simply uses all the concepts that you already understand, and instead of arranging everything in a single list, we arrange things in our mind anyway. We model things on the idea of rows and columns. So our 3 by 3 matrix is going to be now recognized by 2 subscripts rather than a single subscript. So this value that sits here in the upper left-hand corner is going to be known as 0, 0. When we move to the second value in that row, it would be row 0, column 1, and so on throughout the table. It's really not any more complicated than that. When we declare a two-dimensional array, we do it fundamentally the same way as we did with a single-dimensional array. We have to have a data type, an identifier, and then in this case, because it's a two-dimensional array, we have to provide 2 boundary limits. So you see that syntactically we provide two integer values to declare the size of the array. And so if we look at the example above there, we have an array of doubles called sales, and it is 10 rows by 5 columns. When we go to access the items within a two-dimensional array, we, just like we used when we declared the array, we have to provide both subscripts. We provide a row and a column subscript. So the value that's highlighted in this table is sales 1, 2. So we came down to the row 1 and we went over to column 2, and whatever the value is in there, it got assigned to the variable x. Now, as your arrays grow, especially in two-dimensional arrays, numeric subscripts can sometimes not convey the meaning that you want when you're working with that array. And this is where enumerations become especially useful. If we look at the table, the 3 by 3 table there, the numeric subscripts don't really tell me what that value of 1 that's sitting at table 1, 1, tell me what that means. But if I add an enumeration to this table, it allows me to really clarify what that means. So you can see that I've begun to build the mixer array, and I have arranged for my channels to be represented by the columns. So I would have channel 1 through channel 24 in the columns. And then running down the row side, each of the control pots or the faders are represented by their numeric values. So for example, if I look at channel 1, I can see that the volume currently on channel 1 is 11. So that must be the special Derek St. Hubbins mixing channel, because generally it would go from 0 to 10. I am panned a little bit to the left. You see that is a -3 value. My high frequency is set to, and so on across the board. As I look at this, it might be clearer if I arrange the channels as my row values. So row 1, row 2, row 3 would represent the channels, and move the different controls into the columns. But either way, it all works out the same. Now, the mixing board that we're using as an example is an analog board, so I manually control all those, and the settings would stay. On a digital mixing board, this type of an array or table becomes more important, because when I switch that mixing board off, it would lose all of its settings, and as I move from venue to venue, I don't want to have to reset all of the channels. And so a table contains the settings that I used at show A, and when I replug the mixer in at show B, I can recall all of those settings and restore the digital state of each of those controls. So multidimensional arrays, really simple to work with, but a very powerful tool. So in the rest of the video, we're going to look at a little bit of code, and then we're going to talk about a couple of the unique aspects that have to be remembered when we pass multidimensional arrays as parameters to our functions. This example program This example program models the mixer in a compact state. I didn't define all 24 channels and all 15 controls for each one because we would spend too much time just looking at the declarations instead of the code. So let's look at a couple things that I've done here to make the two-dimensional array that we're going to work with look a little bit better. First, I've declared two enumerations. Remember, the enumerations are representing simply ordinal positions in the list. So position 0 is going to be known as channel 1. Position 1 is going to be known as channel 2, and so on across the board. You could go ahead and do these for all 24 channels. The controls, the volume pot, the pan pot, the high frequency, mid frequency, low frequency, and then everything else would be declared as a control within there. So in doing this, instead of addressing my matrix by the numeric subscript values 0, 1, 0, 2, 0, 3, whatever, we're going to address them by a more recognizable name. Here's where I declare the constants that will represent the boundaries of my array. And then finally here in main is where I'm declaring my two-dimensional array. It's going to be called mixer desk. The boundary values, the size of the array, are declared in those two constants. And then I'm initializing every spot in that array to 0. Now that I have my two-dimensional array, let's look at how we would work with that. Really, it's just a matter of adding an additional level of steps. Nothing new, things you already recognize, but one more level to deal with the additional column or row aspect of the table, depending on how you want to look at it. So for example, if I choose menu item R in the program, in order to display all of the table, where before I used a single for loop or while loop to display all of the values of my array in its list form, I now need to nest two loops together in order to plant myself on one row and then display all of the columns within that row, and then only when that's finished move on to the next row, print all the columns, move to the next row, print all the columns, and so on. So you see that I have nested two for loops together. In this case, the controls are going to be displayed at the outset, and the channels are going to be controlled by the inner loop. So for example, we would see all of the volume settings, all of the pan settings, all of those types of things. When I address the array, I have to remember to provide both subscripts, and in this case X is controlled by the outer loop, so that would be my row, and Y is representing my columns, and so that will show me all of the channels for each control. So when we press R, that will display all of the items within the list. In this next little sequence of code, we are filling the arrays. Now what I've done is gone and deck all the values. That means I've set them all to 10 just to get started with the code. Now I've done something a little bit different here. I am going to use the enums as the way of controlling my for loop. Remember that your enums are not actual integer values, they are ordinal values, and so while they will work in their natural form for some parts of the loop, when you get to the incrementing part of it, you have to remember to cast the equation so that it returns back to its enumerated form. So I'm going to say control count starts at volume, which is going to be set to 0. That is, remember, that is the first item in our enumerated list. And I'm going to go until I hit mute. So basically run from the top of the column of controls and run all the way down to the mute button down at the bottom. And then this is where I'm evaluating here, and then my incrementing control. So remember, you have to add the static cast in order to convert this integer addition back to the proper enumerated type. Again, I nest two for loops together, and I do the same thing in here, channel 1 through channel 6, or go all the way to channel 24 if you do. When I address my array, instead of numeric values or numeric variables, I'm going to utilize my two integer values that are set by the control loops. And it does the same thing that the for loop above that used x and y. It does the same thing. In this case, it goes through and assigns values to all of the elements or subscript locations within my array. So we'll execute this program. Doesn't really do anything exciting, but we can see that it actually works. And so if we hit R, we see that the matrix is all set to zeros right now. And we'll go and deck the controls, which is calling the assignment loops. And once we've done that, we'll once again review the control set. You can see that all the controls have been set to 10. It's like a Motorhead concert or something here. Okay. We'll get out of there. And again, there's nothing really complicated about working with the multidimensional arrays. You already know how to control an array through a for loop. Now just think in terms of rows and columns instead of just a list, and you shouldn't have any trouble. In order to pass a multidimensional array, we need to understand something about the way that C++ manages memory when it comes to multidimensional arrays. C++ uses something called row major addressing, and that is that it utilizes a little mathematical formula to figure out where the end of each row is. So it's going to count off the number of columns in order to decide how to start the next row. The reason it does this is that in memory, multidimensional array structures are not laid out as a matrix. They are laid out as a great long list. And so when the program goes to allocate the amount of memory necessary for the structure, it goes out and it finds all of the contiguous memory necessary, and then lays that out as a pointer to the beginning of that and a marker at the end of that boundary location. Or, I'm sorry, your program maintains the marker to the end of that boundary location. When we begin to pass multidimensional arrays, we have to provide to the program the columns marker or the columns demarcation. And the reason for that is that in row major form, the program will recognize the rows by counting off the number of columns that we provide as a parameter. And so you see in this function signature init matrix, we provide the identifier for the array. It's an array of integers, and we provide first the empty square brackets to tell it that it is an array, and then we provide a second set of square brackets, and within that we place the column's number. Internally, the program will then say, starting from the pointer at 0, 0, I'm going to count off 3 integer spaces. So 0, 0, 0, 1, 0, 2, 3 integer memory locations, and at the end of that I'm going to call that one row because it reached the column limit, and then it starts over. So 1, 0, 1, 1, 1, 2 reaches the end of the number of columns, or the amount of memory space used by 3 columns, and then it starts over, and so on and so on. And that's how it decides where our columns are going to begin and end. So let's look a little bit of code and apply that. So I've modified our code base a little bit, and I've added a function called display status, so that code that we were using to display the values of the controls, I've put that now into a function. And you see in the function signature that I am providing the square brackets that tell the compiler that I'm addressing an array, and then a second set of square brackets in which I have put the controls constant. So it knows that my columns are going to be 6 in length. So it'll count 0 to 5 and then start over again, row by row by row. Remember, row major form uses the columns count in order to tell the program where to start reading the next row. So there's my function signature. Nothing really different within the function. I just copied the code down here. You see I use the same function signature here. When I call the function, that's where it gets a little bit funky, but you'll get used to this once you use it. So I commented out all of the display code up here. And when I call the function, once again, all I do is provide the array identifier, and the program handles the rest of it. I do not need to, when I actually call the function, provide the columns count, because I already provided a fixed value for that when I first declared the program, or declared the constants at the top of the program. So when we execute this, it does basically the same thing. If we go and hit review, it's simply going to call that function, and I've added some headers here, but it just shows me the value of all of the matrix elements. And so we've set all the controls to 10 and displayed them. So I think you're going to find that working with multidimensional arrays is really not that complex. If you combine the ideas that you already understand about single-dimensional arrays with your understanding of utilizing nested loops, you're really not going to have any problems at all.
Thank you all very much. Thank you. God bless. Good night.